So armed with that, we should be able to make some progress on this task of finding that string and then uppercasing it. Right? Finding that string and then turning these ASCII bytes into the ASCII bytes that correspond to an uppercased version of these letters, and then printing it out. So there's a new register we're going to have to use to do this, namely SP. Just like for the program counter, we could use R15 or PC. We can actually use SP or R13 to refer to the stack pointer. And so let's use load instructions relative to this SP, this stack pointer, to get the address of the start of this string into a register. And let's talk about each step of that. Okay? So first, we're going to LDR, regular LDR, no B suffix. I used the B suffix in class last week to mean moving one byte at a time. Right now I want a whole word. And the word I want is the word that is at SP, but 8 bytes further. And so this constant that goes in this instruction is always a number of bytes. So the addresses that the assembly language and the machine code talk about for doing memory operations are always in terms of single numbers of bytes. So I'm saying, give me the word that is at the address 8 bytes after this address, which is going to be the address in SP. And we need a register to store that into. I'm going to use R1 as the register that we're going to store this particular address in. So now the address 70FFFD99, right, the corresponding address to that word is stored in R1. That should be the contents of R1 after this line. Okay. Take a minute. Think about what's going to happen next if our goal is to uppercase this string based on what we did on Wednesday. Even pause the video for a minute if you want to think about that for a minute. Okay, so the plan we had in class was to build a loop that would have an index for which byte to be looking at, and keep incrementing that index, inspecting the character at that index, and changing it to uppercase if necessary. So let's use R2 as our index. So I'm going to start R2 at number 0. Okay. There were, depending on if you were in an early section or the late section, we wrote this starting at a late index and counting down, or starting at an early index and counting up. I'm going to start this at an early index and count up because I'm going to want to make a point in a minute, which is we don't know how long this string is. I mean, I know that the one that I used here was 23 long, right? Because I checked in the output and I could count these number of characters. But if we want this program to work for anything that you type in as a command line argument, for any string that you type in as a command line argument, that has to work for different length strings. And there's something special about the way this information was put here versus how we put it with ASCII, which is this 0, 0 at the end isn't by accident. It's not by accident. What's actually happening here is this sequence of bytes is encoded as a string the way C sees a string. Okay. So in the C programming language, and in a lot of low-level context, so I'm going to call it a C string, is a sequence of ASCII bytes ending in 0, right? Ending in actually the byte 0, not like the ASCII that encodes the number 0, but ending in 0, right? Like really hex 0 is going to be the value in that last byte. So a rule for processing strings that are formatted this way is when you get to that 0 byte, you can stop processing it because you know it's the end of the string. And this can be useful for calculating the length, anything that processes character by character. So what we're going to do is we're going to count up indices, look up 1 byte at a time, and when we get to that 0 byte, that's when we know we're going to stop. Okay? So we're going to have a loop, and every time we go through the loop, this is where we're going to use that instruction we had, load 1 byte. I'm going to use R3 as the register where we store the character. And think for a minute about what I'm going to write for the address to look up a byte at to get the current character. Think for a minute about how I'm going to do that before I type it. Okay, so I'm going to use the address where we've stored, the register where we stored the address of the string. So remember, we loaded from R1 basically this address, which is the address of the start of the string. And I'm going to offset that by whatever value is in R2. Okay, and R2 is going to start at 0, and over the course of this loop, we're going to be incrementing R2 to keep pointing at the next index, and so on. Okay? So after this, that single byte is in R3, and the check we need to do to see if we should continue this process of uppercasing, the first thing we should do is make sure that this isn't the 0 byte that's at the end. So I'm going to, which one do I want? Do I want test? Do I want compare? Which one do I want? I'm going to compare R3 against 0. And if those were equal, I'm going to jump to the end of the loop. And so I'm going to insert a new label here and for what we do afterwards. And we'll just, this line means these two lines together are saying stop when we get to a byte that is all 0. Okay. All right, so now we know we have the byte we want in R3. And I'm going to make an assumption here that we're going to type in things that are in all lowercase to start. We can come back and refine this to do more checks, but to keep this program simple, what I'm going to do is just subtract from R3 decimal 32, which I believe is the difference between upper and lowercase ASCII. So this does the actual lowercasing, the actual uppercasing, sorry. Okay. And I'm doing that just because I don't want to add a bunch of extra conditions here that obscure the memory operations that are the interesting part of this. Okay, so we subtract that, we're going to get an uppercase character back because uppercase characters are lower in ASCII. And then we need to store it back. So I'm going to store a single byte and think about for a minute what the arguments to the store are going to be before I type them. Okay, yep. I'm going to store R3 into the address at R1 offset by R2. So these two instructions mirror each other, and that's an intentional mirroring. This one is looking up the value and putting it in R3. Store, we read in the opposite direction. The value in R3 is being stored at this memory address. So the thing in brackets is always referring to some memory address. And in this case, we're getting it out of memory and storing in the register. In this case, it's going from a register to memory. So that stores it back. Okay. Now we should increment the value we have that we're using as our index. And then I'm going to do, the way I've set this up, we'll unconditionally go back to the beginning of the loop. So we'll loop, 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 and the only way to leave the loop is when we finally hit that 0 byte. Okay? And at the end, I'm going to add the little bit of system call magic we need to print it out. So R1 still holds the address. So we're going to move into we'll do R0, we'll print out R1. R1 already holds the address that we want. R2 is going to hold. Ooh, we need the length here. We need the length here. Do we have the length anywhere? Do we have the length? Yeah, R2 actually holds the length. So R2 already has the right value for the length. So this is, if we remember, this is, I'm recalling some stuff from over a week ago. This is the number of characters to print. I'm going to put all the things in here. 1. This is the address of ASCII bytes to print. And this 1 means, oops, 1 means print on standard output. Okay. And then we move R7, and I believe it was number 4, was do the printing operation. And then if we do the system call with those settings, we should get a print out of it. Okay. Make the print happen. So actually, let's say this is choose the printing operation. Okay. So let's. I'm first going to do a quick run of this to see if it works, and then we can go back and step into it and see what happens. So if it doesn't work, I want to use the debugger to figure out what we did wrong. Okay. So let's quit out of this. Let's go back to our build commands and rebuild and relink. And now we should be able to do uppercase on hello, and we should get back hello. There we go. We did get back hello. Cool. So this does seem to be working. It's worth going through one iteration of this loop in GDB to convince ourselves that we understand where all these pieces are coming from. Okay. So I'm going to GDB, and remember I need this --rs option. We're going to go to layout reg, and we're going to break on. I wonder if I put the star here, if it'll do the thing that I want. Maybe I just. Oh no, it still says line 9. I bet that's going to be off. Let's see. Oh hey, that does look right. Cool. So I guess that's interesting. I wonder what goes wrong with that without that star. I don't really understand. Okay. But let's start stepping through this. So this is looking at our load instruction at the beginning of our program. If we step past that, think for a minute, what register do you expect to see change and how? What register do you expect to see change and how? Okay, the R1 register should change. The R1 register should change, so that's the target of the load. And it should change to whatever is at this address. And remember, the way we can peek at that before this runs is we can look at memory around the register we're using as the base address here. So we should expect to see this 70FFFDAB show up in R1 after this instruction runs. So let's do that. Okay, so that address indeed does show up there. And the only other thing that changed is that our program counter moved forward. And so now we can go into the loop because this is just initializing R2. Now in the loop we can think about what this is going to do. We can peek at memory here before we actually run this instruction by using $R1, because R1 is the address that we're looking at here. We should ask ourselves, what is the byte at R1 offset by the value in R2? Should be, well, it should be this byte, because that is the, we're thinking little endian here, so this is the first byte, or the 0th byte of this word counting up. Okay. So we should expect to see, after this instruction, 68 show up in R3. Okay. So let's see if that's what happens. R3 did indeed get hex 68. So that's the lowercase, I think the lowercase h in our hello. That makes sense? Yeah, that's 7 or so past 61, which we were seeing earlier, and that was A, so 68 makes sense, so that's H. Okay. That's not 0, so the comparison will only set the, let's see, this comparison set the carry bit because we did why would this set the carry bit? Because we subtracted, I am not positive why the carry bit was set there. I would have to go read a little bit about compare to convince myself. The thing that I really care about is that the z bit isn't set, which definitely isn't for 2 being set. But I'm not positive why. I was actually expecting nothing to be set there. So I'm curious why the carry bit was set, but I could just be a little confused about what compare should do right now. I want to press on, because that's not the interesting part of this program for us. So what this is going to do is, if the 0 bit is set, we'll jump all the way to the end. And the 0 bit isn't set, because that would be the 4's place of the CPSR's leftmost digit here. So that's not set. So this is going to step right by and go on to the subtraction. Then we should do this uppercasing conversion, which is going to change R3. So I is on R3. That's what's going to change. Okay. And then this is interesting to think about how we'd observe this change. Because when the store instruction runs, we're not going to see a register change. Because what store does is it takes this value from the register and puts it at this address in memory. So right now we know that this is what memory looked like around R1. So if we step, so if we can run that command again too to make sure that's what it looks like right before we run this command. That's there. And then right after we run this command, right, the only thing that changed in register is the program counter. But if we compare the output, we see that the 68 here turned into a 48 here. Right? And that's the only difference. So the entire effect of this instruction was to change that 1 byte from 68 to 48. That's what subtracted the 32. That's going to make it act like an uppercase character now. So then we increment our index register. We're going to unconditionally loop, and then that loop is just going to keep going. And we could set a breakpoint at end and continue, and that's going to run all the way through the loop until the end. We see that R2 got set to 5, which is good because that's the number of characters in hello. R3 ended with that 0 byte. There was eventually a 0 byte in R3. And the CPSR ended up with the 4-bit being set, indicating that the 0 bit was set, which is why we left the loop. And then the rest of this is just going through the motions to make sure that we can see the output we wanted to see. Let's see. I don't know if we can see that output in GDB or not. I don't see a capital hello. Oh, yeah. So one of the things that'll happen in GDB sometimes is, here's low up here, right? Is when you're using GDB and you're using output. GDB is like trying to do manage all the output for your terminal. And so you'll sometimes see these weird interleaving things where standard out shows up somewhere on the screen. I'm poking around for good answers to that. If you run without the -TUI option, the output appears in more reasonable places, but the layout doesn't work as well, at least in my terminals on OS X. But it did print out. It printed out in a really weird place. It's not part of program counter or anything like that. This is just having to do with the terminal printing out in an odd spot. So we can step through the rest of this, and we can watch as we evaluate the last instruction, and that says that the process that we were running exited normally. Okay, that is a little taste of where command line arguments go in memory. We saw hello go somewhere in memory. And a complete example of using these memory operations to do this. Again, this will work for any length that we pick for the input word. So if we said something like, well, if we did our long list of A's from before, right, we should expect that to print out a bunch of A's. If we had our something like ARM, we should expect a short string to work too. Note that these are printing out without any new line at the end of them. There was no new line in the input, so there's no new line in the output that comes out, which is why you're seeing my terminal prompt not be on a new line. That's just because there's no new line at the end of this output. And we can talk more as time goes on about how to manipulate strings better. But that's a taste of these C-formatted strings. So one of the big things we just saw is that we have these C-formatted strings, which are a sequence of ASCII bytes that end in this 0 byte. And we see that we can use both a load that loads a single word and loads and stores that work with bytes to do this ASCII conversion. And we also see that a little bit about how GDB decides, or not how GDB, but how the process gets laid out in memory, and how we can see that in GDB for where these command line arguments go.